Now, for this exercise, let's start learning how to read. So the first thing this is telling me is that a biologist is researching a new bacteria. At time 0 hours, he puts 100 bacteria into a favorable growth medium. So what is this first sentence telling me? At t equals 0, meaning at the beginning, I have how many bacteria? 100 bacteria. So at the beginning, that is my initial condition, is 100. Now, 6 hours later, I have 450 bacteria. So, after 6 hours, that is when t equals 6, I have a growth of 450 bacteria. Assuming an exponential growth, meaning my base is e, what is the rate of growth for the bacteria? So what I'm being asked is, first of all, to find the rate of growth for this model. So we're going to find the rate of growth, and there we're going to write the actual model, okay, to have everything at hand. So to do that, remember, first off, we know that after 6 hours, I have 450 bacteria. So 450 bacteria are found when my time is 6. My initial data is 100, and the rate of growth is what I'm looking for. So again, this is an exponential equation where I want to find the value of one of the terms in the exponent, so I have to solve this exponential equation. But now you already know that you have to pass everything dividing to the left side to leave the exponential term alone. Then we're going to apply logarithms on both sides of my equations. I'm going to pull down the exponent. By now you already know this is 1, so this leaves me with ln of 45 over 10 equals r, and 6 passes dividing. So my rate of growth is this number. So the actual model is going to look like this. Is a bacteria. So the number of bacteria at a certain moment is the initial number of bacteria times my base raised to that growth exponent, growth rate times time. So this is the actual model. Now, I'm being asked at what hours will we have 1,000 bacteria. So again, let's read. I'm being asked hours. When I have 1,000 bacteria, meaning I'm being asked time. So if I'm being asked time, I have to know the other incognita, that is a certain amount of bacteria. And in this case is 1,000. So 1,000 bacteria are going to happen when we solve this equation. And to solve this equation, as usual, first the incognita is in the exponent, meaning we have to solve for t. So first off, let's leave the exponential term alone. So this is 1,000 over 100 equals e to the power of ln of 45 over 10 over 6. So now that I have my exponential term alone, I can apply logarithms. And first off, I can simplify this fraction. This is 1,000 over 100. We can cross off some zeros. So this is 10. So natural logarithm of 10 is natural logarithm of e to the power of ln of 45 tenths over 6 to the power of t. Now, I can pull down that entire exponent. It doesn't matter if that exponent has already logarithms inside of it. It doesn't matter. So this is natural logarithm of 10 equals the entire ugly looking exponent times ln of e. As usual, this is 1. So if I want to solve for t, this is ln of 10 equals, I'm going to pass this entire term dividing, so this is ln of 45 over 10 over 6. So this is the time when we will have 1,000 bacteria. Notice that I have a bunch of logarithms dividing each other. It doesn't matter. As long as you can identify that this is a coefficient in the exponent and we can pull it down with logarithms.